that is the revealed phase transition in this magnetite is correct. What we're interested here is the magnetic ordering transition in this material under high pressure. Here we can find when the pressure is increased, the volume will decrease. And the magnetic energy, that is the energy between magnetized state and the non-magnetized state, decrease. This is reasonable. And for the magnetic moment in the two sublattice, that is A sublattice and B sublattice, in both sublattice, the localized moment decreased. This is also reasonable. But for this material, two sublattice magnetic moment coupled antiferromagnetically. So the net magnetic moment we can find as we increase the pressure, it will decrease first and then recover a finite value and still a little increase even at the pressure of 100 GPa. So what experimentally observed is this state. We use XMCD to examine the high pressure dependence magnetism. We can find a very deep transition from ambient pressure as we increase the pressure. Theoretically, we can identify this rapid decrease in magnetization is associated with the phase transition from ambient pressure phase to the high pressure phase, which is labeled by black and blue dot respectively. But for the more high pressure phase, we can find the net magnetic moment recovered a finite value. This has been explained the asymmetry of the two sublattice. That is, even for both sublattice, the localized moment decrease as the increase of pressure. But the net magnetic moment, which is subtraction of two sublattice, will recover its finite value. Unless we apply very extremely high pressure, that is, in both sides, A side and B side, the spin state is a low spin state. The system will be non-magnetic. So this picture gives us information of the spin state for the ion at the A side and B side. For the A side, the valence state is travelant. For the B side, there's two kind of ion. That is a diamond and travelant. The orbital occupation is listed as following. We can find as we increase the pressure, the system or the sublattice magnetic moment will transfer from high spin state to the intermediate spin and then to the low spin state. But due to the asymmetry between two sublattice, the system will recover a finite magnetic moment even at very high pressure, experimentally observed. So our finding has provided the first theoretical result for the magnetism or the spin state at the high pressure. And this finding is very maybe useful for the psychology. Since this magnetite is composed in many mineral materials and will influence the magnetic field around our Earth. So this is an example of our first principle calculation of pressure dependence of crystal structure and electronic structure in magnetite. Finally, I will introduce our recent work on the ferroelectric photovoltaics. As we know, for the energy demand, green energy is very important, and therefore the so-called photovoltaic solar cell has attracted wide intense interest in condensed matter physics as well as material science. So the solar cell is usually composed of a semiconductor with a band gap of Eg. It will absorb the photons with energy higher than the energy band gap. But for the photon with energy higher, we can find the excited electron will relax to the bottom conduction band. So there's energy loss. So this is called formalization. So in this picture, we give three lines. The outer line is the outer is sound spectrum. After formalization, we can find there's energy loss after the formalization. In addition, formalization, there is a relaxation of the excited electron in the system. There's also so-called voltage loss of the solar cell. This is due to, in addition to absorbing external photons, the system will emitting photons at the equilibrium state. So there's a voltage loss. So the total output of the system, depending on the energy band gap, with the so-called Shockley Pierce limit. So in this picture, this line gives Shockley SQ limit as a function of a band gap for the material. And we can find the most favorite band gap is around 1.4, with the maximum power conversion efficiency of around 34. And this picture gives many examples of nowadays efficiency of these semiconductors. But we can find all these materials are based on conventional semiconductors. So why we should study ferroelectric materials? For the ferroelectric materials, experimentally has found a very large output of the voltage. This is due to the spontaneous ferroelectric polarization developed in this material. This picture gives a conventional solar cell based on p-n junction of a semiconductor, where the electron and holes are separated by the intrinsic electric field in this p-n junction. But for the ferroelectric-based solar cell, the intrinsic electric polarization in this ferroelectric material will facilitate the electron hole separation. In addition, the electric polarization will provide a large output of the photo-induced voltage. But unfortunately, most of ferroelectric material is composed of oxide. As I mentioned before, oxide material is very dirty. It contains large amount of defects, and therefore providing many recombination center and decrease the power conversion efficiency. The situation changes until 2 years ago. A group grows high quality a multi-ferric sample with the solar cell. The power conversion efficiency for the single junction has reached as high as 3%. For the multiple junction, the power conversion efficiency is almost around 80%. This is the highest power conversion efficiency ever reported for this ferroelectric system, and their findings is very exciting. And after this, many groups has moved to this ferroelectric photovoltaics to provide upgrading of the power conversion efficiency. On the other hand, for the photovoltaics, when we introduce the spin degrees to freedom, we can realize many novel function energies. For example, here is a demonstration of the so-called spin photodiode effect. And the right panels gives the information of the so-called photospin photovoltaic effect. Therefore, what we proposed is a multi-ferric photovoltaics. In the multi-ferric materials, both the ferroelectric polarization as well as the spin degrees of freedom exist. So we can utilize both degrees of freedom to realize not only the high efficiency of power conversion, as well as lower functionality. For example, the spin-dependent current or the ferroelectric control of the photo current. And in fact, in our recent work, we have identified a novel material that is calcium ion chromium double perovskite oxide. And in this collection of the ferroelectric photovoltaic material, the larger the ferroelectric polarization, the better the system. In addition, we should have a very reasonable optimum band gap as silicon around 1.4. And what we have identified, this double perovskite satisfies the criteria very well. It has a proper band gap as well as a large ferroelectric polarization. So compared with conventional ferroelectric oxides, it has a suitable band gap. And compared conventional semiconductors or all recently organic perovskite structure, it has a large ferroelectric polarization. So what we have calculated is this crystal structure. It contains alternatively chromium and iron along the C directions. And in the polar phase, we can find the chromium and iron displaced away from its center. So a ferroelectric polarization will develop along the C direction. This is its central symmetrical system. And based on the initial method, we can find the most exciting change when we introduced parent material, for example, calcium ion or the calcium chromium. The most important result is reduced band gap within around the 2 electron volt. In addition, we can find the band gap, the electronic state near the band gap is spin polarized. Therefore, it provides a chance to realize when a photon is absorbed, the excited electron and holes is fully spin polarized. So we also calculated the optical absorption of this system as a function of the concentration of the ion or chromium. We can find that the most important thing is for the double perovskite structure, the absorption matches the sound spectrum very much. So we can find for the parent compound, the absorption usually starts from the violet region. That means the system is a wide band gap insulated. For this double perovskite structure, we can find it starts from 2 electron volt and absorb most of the sound spectrum. So in addition, we have studied the disorder-dependent absorption spectrum. We can find, in this case, the absorption do not depend strongly on the disorder in this double perovskite structure. Besides a suitable band gap, large ferroelectric polarization, and a nice match with sound spectrum, as well as the net magnetization. We have also found that the power conversion efficiency is very high for this double perovskite structure. And usually for solar cell, the absorber is around several hundred nanometer. And in this case, in our system, the photon conversion efficiency is already around 30%. This indicator can be regarded as the upper limit of the power conversion efficiency. We can also we have also calculated the spin-dependent absorption spectrum. We can find, for example, in this 50% material, in a wider range of energy window, the absorbed is mainly one spin channel, and the photo current should be spin polarized. And finally, we have shown the photovoltaic performance of this double polarized based solar cell. To do this, we have constructed a sandwich structure which composed semiconductor. That is, here is a multiferric double polarized as well as two electrons. In this structure, we have calculated the transport properties using the first principle input date. And finally, we have this result. We can find the ultimate power conversion efficiency is around 10%. And the maximum thickness for the power conversion efficiency is around 100 nanometer. This is according with experimental observation, usually at this thickness. And the most important finding is almost reach 10% of power conversion efficiency. So this example has provided a fact that the polar transition metal oxide could provide a very useful example to realize high efficient solar cell, and as well as novel function. In this case, we have realized spin polarized photocurrent in this double polarized based solar cell. Okay. Finally, I will show recent experimental findings in transition metal oxide heterointerface. That is, in previously study of transition metal oxide and the heterointerface, people seldom discuss the effect of spin orbital coupling. The reason visiting here this time is to learn spin orbital physics with Professor Guo. And in this system, experimentally, we have realized spin to charge conversion in this transition metal heterointerface. And we have injected a spin polarized current, and the output is a charge accumulation at the interface. The physics behind this phenomena is spin orbital coupling, that is the Rushbar effect at the heterointerface. In fact, the Rushbar effect has widely discussed in conventional semiconductors, but for transition metal oxides and their heterointerface, I think field work was done. So there are still many room for us to do theoretical research to find more efficient spin to charge conversion or charge to spin conversion. So we hope we can study this project further. Okay. Finally, let me thank my collaborator. Besides my colleagues and my groups in Sheng Ju University, I would like to thank particular thanks to Professor Wen Ji and Wang Fa in Peking University, as well as Professor Guo in NTU. I also like to thank academician Gong Changde in Nanjing University. And this also supported by National Science Foundation of China, as well as 973 programs in China. Thank you very much.
Okay, is there any questions? I'm sorry for the delay today. So you mentioned that you have this spin 1 superconductor with no charge.
It is a spin superconductor.
A spin, though, can you elaborate more about this? How are we going to use this?
In fact, it stems from a theoretical paper provided by Xie Xingchen and Sun Qingfeng in Peking University. it describes extone state. Conventional extone state. Okay, sorry. Conventional superconductor is composed Cooper pair with a charge 2 and a spin 0. But in their theoretical framework, they composed charge 0 and spin 1 pair. It is a little like extone pair, but it has a total spin 1. So they argued in the low temperature, they can condense and to form the spin dissipationist transport. But the exact theoretical treatment, I was not, still not familiar with. But what we observed in this particular superlattice structure satisfied the proposed situation.
Any question? But you showed a few experimental results. Is that experimental results pop, or do you have a collaboration with your work?
Which one?
Because you show some experimental.
Experimental results?
Yes.
Which one?
There are so many, I cannot remember.
Okay. All this in the introduction is experimental.
And this is actually after they publish it, and you see this.
Yeah.
Okay. So I know the Guanyu has some collaboration with experimentals.
He has introduced me a recent publication with Professor Zhu in Condensed Center for this system.
Any question? Alright, if not, then send speaker. Again.需要一些实验证据，所以才需要这个实验家。是的，你可以讲那个，实际上还是有问题。
都是讲的。对。
但是很多人想知道说，它很多现象是在实验上印证。
有的时候理论上先做，但是可能实验上做不出来。后来我实验再做出来，然后发现
先退嘛。
那张
同时就要先退，然后那张
做一些超前的东西，算了，就是这样子。
哦，对了，然后下礼拜交期中报告呢，1页或者是1000到500到1000字，谢谢。对，下礼拜交。因为好像没有那个，没有
我不知道他们有没有。这好，因为
实验还没有关。
实验应该他们在推这个概念，但是据说好像刚过来很多不太同意他这个东西。他们之前是因为他们都是做低位差，就给你加一个强磁场，能实现这个。但是我正好我们有一个同事是从他们组里出来，然后我们交流的时候，他说你这个东西好像跟他那个理论上提出来的很一样。我说这个好，那我就顺便来讲联系一下。
实验学家就可以做了。
对。他们当时提出来，他们也提了实验的realization，就是要很强的磁场，然后我们直接可以
从我记得是上在更之前的话好像没有讲。
上次因为出来的可能那个每个人看一个。
期中报告是500到1000字吧
500到1000字，对。
下周的话交哪？
我会在那个系统上面跟大家讲，要交哪。
行，好的。对了，然后你说这个上课的这个